higher order derivatives. We have done a lot with the derivative, or the first derivative is another way to say that. We also, for example, have the second derivative and some notation here. You may see y double prime, f double prime of x, and then d squared y over dx squared, or d squared f over dx squared. What this means is you just differentiate the first derivative of a function and you get the second derivative, okay? And similarly, you could have a third derivative. The notation would be y prime prime prime, or f prime 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 of x, or d cubed f over dx cubed. Let's see, let me match it with above, or like this. And you can keep going. You can keep differentiating. Generally, the nth derivative maybe I will just write one of the notations. People will often write a parenthesis like this. Okay, now let's mention an important application where we do see, and we have seen even earlier in the semester, we have seen the notion of a higher order derivative, and that is when you have position function, p of t, and this is motion along a line. Then the velocity is the first derivative. V of t is p prime of t. And I mentioned acceleration is the derivative of velocity, but interpret it as a higher order derivative. This is the second derivative of position. And then there's one more you might see in a physics class. It's jerk, j of t. And this is the third derivative of position. So these are all things that come up when you have motion along a line, which is really how we started the semester, and it's an important application that we return to. We see this is an important use of the first, second, and third derivative. Okay, now higher order than third. Where do we see this? I would say probably not much this semester, but finding the nth derivative of a function comes up a lot in Calculus 2, something called Taylor polynomials and Taylor series. Okay, let's do an example. Here's an example. We are given f of x. We want to find f prime and f double prime, the first and second derivatives. And I mentioned in the last video that even though, well, the very next class will be starting the rules for derivatives, we may use the power rule for today. And, well, last time where we did extrema, intervals of increasing and decreasing. So I'm going to use the power rule here. One thing that I can do to this term, so let me rewrite this slightly. This is 6x to the minus 1, and now we can use the power rule, okay? F prime of x here, well, the constant comes along, so we have 15 times, and then bring down the 3x to the 2, and then plus 5, bring down the 2x to the 1, plus 6, bring down the minus 1, x to the minus 1 is negative 2. Okay, so the first derivative is 45x squared plus 10x minus Well, it's 6x to the minus 2. We could write this as minus 6 over x squared, but especially because I'm going to differentiate again, I will leave it like this. Now immediately I can write down the second derivative. Well, it's a power rule again on each term. This would be 45 times 2x plus 10 times derivative of x is 1, and then minus 6, we bring down the power, x to the minus 2 minus 1 is negative 3. And finally, we have, this is 90x plus 10 plus 12x to the minus 3. Okay, so here are the first and second derivatives for this function. Last time we saw, well, let's say you have an open interval I. If the derivative is positive on I, then f is increasing on I. And if the derivative is negative on I, then f is decreasing on I. And so, well, a theme of last time, which came from this, was we can use the first derivative to address questions of increasing and decreasing, right? That's exactly what this says. Now, the question becomes, what about the second derivative? So what if the second derivative is positive on an open interval I? What can you say about the original function? We know the second derivative is, now I'm gonna mix the ddx and the prime notation here just to make a comment. It's the derivative of the first derivative. The second derivative is the instantaneous rate of change of the first derivative, or we know the first derivative gives us slope of the tangent line, okay? So the second derivative tells us how the slope of the tangent line is changing. Okay, let's think about a picture here. Here is some function, okay? And, okay, maybe here is local min. Well, we know, for example, maybe this is at 1/10. This would be decreasing from minus infinity to 1/10 and increasing from 1/10 to infinity on those open intervals, for example. But that's not what I'm interested in the moment. What I'm interested in is the slope of the tangent line. So for example, here, if I pick a point over here, okay, and then I pick a point here, I can draw a little tangent line, and then here, horizontal tangent line, here, tangent line, here, tangent line. Okay, what do you notice about the slopes? Well, first of all, this is negative, negative, 0, positive, and positive, but it's more than that. This is steeply negative, and then it's less negative. Slope is 0, positive, more steeply positive. So what you see, reading left to right, the slope of the tangent line in this picture is increasing. Slope of the tangent line, the derivative is increasing. This would say its derivative is positive. So in a picture like this, we get the second derivative is positive. Okay, well this shape has a name. It's called concave up. So this is the answer to the question. Answer to this question, what if the second derivative is positive on an interval? Answer, the original function, f of x, maybe I should write that here, is concave up. And the way I think about this picture, okay, it goes like this. Concave up like a cup. Okay, that's the way I remember the shape of concave up, second derivative positive, concave up like a cup. And the shape is like this. But you don't necessarily have both sides. You could just have just this side of the concave up, okay? And that would still be concave up. Or you could just have this side of the concave up, this one, and it would still be concave up, okay? But this concave up like a cup, second derivative positive, very nice. Let's ask the same question about when the second derivative is negative on an open interval I. What if the second derivative is negative on I? Let me draw the picture and then I will discuss. So it would be something like this. Now, oh, pardon me, here the max is maybe at negative a tenth. Okay, so here we are, just to think about the topic of yesterday, the function is increasing from minus infinity to negative a tenth open interval, and then it's decreasing from negative a tenth to infinity. Okay. Local max at x equals negative a tenth. Very nice. But let's get to the question here, which is what if the second derivative is negative? And just like we saw with positive, this is the picture, but let me tell you why that's the case. Let's think about it like this again, where the first derivative is slope of the tangent line, and the second derivative measures its rate of change. So here, I have a tangent line. Here, tangent line. Here, horizontal tangent. Here, tangent line. Oh, and then here, tangent line. Okay. What we see here, well, for these two, we have the slope of the tangent line is positive, 0, negative, but it's the steepness, right? It's very positive and then not as positive, 0, sort of negative, more negative. So the slope of the tangent line for this curve, reading left to right, it's a decreasing function. So in this picture, the second derivative is negative, okay? And this too has a name. I'll match for answer. The function is concave down, okay? So we had concave up like a cup. What do you think this is? Concave down like a brown. You got it? Okay. So here we have this picture, this shape, and you could just have one side or the other side. It's fine. You don't have to have the full frown. But this shape, concave down, like a frown, second derivative is negative. Okay, and that's what the second derivative being negative on an interval tells you, concave down. Okay, now there's one more thing that I want to mention here, and that is the notion of an inflection point. An inflection point, now you will either see the inflection point as being the x value or the point on the graph, just depending on the context, but an inflection point is where the function switches concavity, which means on one side of x equals b, or the point b comma f of b, the function is concave up, and on the other side it's concave down, or maybe it's concave down on this side and concave up on this side. Okay, so the second derivative is switching from positive to negative at this x value, and this means the following, that the second derivative at b is either 0 or does not exist. Okay? So to find potential inflection points is very much like looking for critical points for the function, except you're working with the second derivative. So if we wanted to find inflection points, which I'm about to in an example, you would set the second derivative to 0 or does not exist, and then actually check that on one side the second derivative is positive, on the other side it's negative or negative positive, like this. Okay, so let's do an example. Let's do an example now. Okay. Here's our first example, and this one came off an old final exam, and I used the wording exactly like the final. We will, in part A, determine the intervals where the function or the graph of the function is concave up, and then similarly intervals where the function is concave down, and then we will find inflection points. And here it specifies x coordinates. Okay, so what we need really is the second derivative, because this is what tells us about concavity. So part A, well, this is a half x to the fourth. Right, so when you differentiate, this is power rule, this becomes, well, 4 times a half is 2, x cubed, and then we have 6 times 3, 18, x squared. Immediately, I will take the second derivative, because you see the question does not ask about increasing, decreasing, or local max and min, so I'm not going to need critical points. I'm not going to need the first derivative for really anything except as a step to calculating the second derivative. Okay, now I differentiate this. I get 6x squared, and then 2 times 18 is 36, like this. I'm going to be setting the second derivative to 0 or looking for places where it does not exist. That's the possible places for inflection points. But this function is defined on the whole real line, which is the domain of this function. So I really need to set this to 0. But first I will factor. I can factor out a 6x, and then I have x minus 6. When I set the second derivative to 0, the only possible solutions are 0 and 6. Okay? Now, don't just say immediately these are inflection points. They might be. We need to actually see that the second derivative switches sign at those points. And I need to understand that anyways to address part A. So what I will do is very similar to intervals of increasing and decreasing, except we're working with the second derivative. But I divide the domain into intervals based on where the second derivative is 0 or does not exist. This would be minus infinity to 0, 0 to 6, and 6 to infinity. And then I want to test the second derivative. I have x. The second derivative factored is 6x, x minus 6. And then the second derivative. Okay. Pick a point in each interval. Here, for example, I'll use x equals -1. Here, I'll use x equals 1. Here, I'll use x equals 7. But again, what matters to me is the sign of the second derivative. So you can really pick any point in this open interval, any point in this one, and similarly any point in this one. Okay, so we have -1, 1, 7. 6 is positive, this is negative, negative, the second derivative is positive. 6 is positive, positive, negative, second derivative is negative, and then positive, okay? We have, let's see, positive, negative, positive, okay? So this tells us my original function is, part A, good, concave up. On the following intervals is where I see a plus, minus infinity to 0, and 6 to infinity. And is concave down just on this one open interval, 0 to 6. Okay, this is part A. And then I'll put my final answers in this box. Part B, inflection points. Well, you see, looking at this number line, concave up on this side, concave down on this side, x equals 0 is an inflection point. And then similarly, at 6, concave down on this side, concave up on this side, x equals 6 is an inflection point. Okay? Let's look at this example where we have a function h of t, and we will do both. We will find intervals of increasing, decreasing, which was the focus of the last video, and we will do intervals of concave up and down, which is really the focus for today. And then we will look at a graph of this function and try to make sense of what we found in part A and in part B. Okay. Well, first, intervals of increasing and decreasing. This involves the first derivative and critical points. So we need to calculate the derivative, 5t to the 4th. I'm using the power rule. Minus 5 times 4 is 20t cubed. And then, well, I'll write plus 0, although you don't have to. It's 0. But the derivative of a constant is 0. And then let's see what I can factor out. I can factor out a 5t cubed. And I get t minus 4. So when I set this to 0, I get t equals 0 and 4. And of course, this derivative is defined on the whole real line, so we never have a place where the derivative does not exist. These are my only 2 critical points. Okay. Now, I'm doing increasing and decreasing. So I have 0, I have 4, and I'm going to test the derivative. I have t factored, it's 5t cubed, t minus 4, and this is the first derivative. And I can immediately write the intervals, minus infinity to 0, 0 to 4, and 4 to infinity. These are our open intervals that come from dividing the domain based on the critical points. Okay, so then I pick something in each interval. Here I will pick t equals 1. Here I will pick t equals 5. And here, for example, let's do -1. And now I will test the first derivative because I'm in part A. -1, 1, and 5. Okay, 5 is positive. This is negative, negative. The first derivative is positive. At 1, 5 is positive. This is positive, negative. First derivative, negative. And at 5, we have positive. Okay, so what do we see here? We see this is increasing. Now, this is the original function. I'll write it just to make sure we know. And I could put my pluses and minuses. We have plus, minus, plus, like this. So h of t, my original function, is increasing on minus infinity to 0 and 4 to infinity, and it's decreasing on 0 to 4. Okay, so this is part A, and what I will do is I will just recopy part of this, and then we will move on to part B. But maybe before I do, just as a comment, I will do my comment in purple. Look, at 0, we have plus, minus. We are increasing and then we're decreasing. So we have a local max at t equals 0. And similarly at 4, we are decreasing then increasing. We have a local min at t equals 4. And we will see this when we look at the graph, that we have a local max at t equals 0, a local min at t equals 4. Okay, great. Now let's move into concave up and down. I have erased so that we may work B, but I recopied what we calculated for part A, the increasing and decreasing. Okay, and then I probably should have kept the derivative, but I can calculate it quickly. This we had for h prime of t. Now I move into B, concave up and down. I need the second derivative. So I differentiate the first derivative, 20t cubed minus 60t squared. I can factor out 20t squared and I get t minus 3. So here the second derivative is defined on the whole real line, exists everywhere, but the second derivative is 0 provided t is 3 or 0. Okay, so now 0, 3, okay? My intervals would be minus infinity to 0, 0 to 3, 3 to infinity. And now let's check, okay? We need to check, what are we checking? Second derivative. So I need t, I have this factored, and then I need the sign of the second derivative. And again, I will pick something in each interval. Let's use t equals -1. Let's use t equals 1 and t equals 4. Okay, -1, 1, 4. This is positive and positive. When you square, t squared is positive for all three of these. Now this is negative, this one is negative, and this one's positive. We have negative, negative, positive. Okay? We have negative, negative, positive. Oh, this is interesting because look, this is not an inflection point. So we have only one inflection point. Is where? Right here at 3. Let me write this underneath. The only inflection point is at t equals 3 because it switches concave down to concave up. Or if you speak of it in terms of second derivative negative, second derivative positive. T equals 0, even though we had second derivative 0, the second derivative does not switch sign. We do not go from concave down to concave up or concave up to concave down, so 0 is not an inflection point. And this is an important observation. So now let me just finish this maybe over here. The function h of t is concave up only on one interval, 3 to infinity, and it's concave down well, I personally would accept two different answers. You can either just list the intervals like this. That's perfectly fine. It's how it was divided, okay? Another way you can list, maybe I'll do this in blue, you could also just put them together. I would accept this answer as well, okay? So here we have concave up, concave down, increasing, decreasing, and I'll move out of the way, but now let's look at a graph of this function and try to interpret what we have calculated using calculus. Here is the function h of t in black that we just looked at. Let me get the spotlight. Okay, we had, let's see, if I look at what we just calculated, we saw it was increasing from minus infinity to 0, and then increasing again from 4 to infinity. We saw it was decreasing from 0 to 4, right? And I mentioned as in a little side work that we had a local max at x equals 0. We see it here on the graph, 0, 8, that we have a local min at x equals 4, and we see this on the graph, 4, negative 248, okay? Then this point, 3, negative 154, or at x equals 3, this is our only inflection point. And you can see this shape here, this concave up like a cup. We see it in the graph. Of course, we calculated it using calculus and second derivatives, but we see this concave up shape. And then similarly on this side of 0, we see concave down. And on this side of 0, we also see concave down, okay? So 0 was not an inflection point because the function h of t does not switch concavity there, even though the second derivative is 0 at t equals 0. This is the behavior that we calculated. It's really nice to connect it back to a graph. Let's end today by thinking about shapes that can happen when we have second derivative positive, second derivative negative, and then we will vary whether or not the first derivative is positive, negative, or 0. Okay, so what I have graphed, you can really think about, I'm just looking at, well, 6 different functions right around on an interval right around x equals c. And the functions are graphed in purple, and then my brown underneath with c is like my x-axis. You can think of it this way. Okay, so what do we see here? Well, the first row, this is this cup shape. We have just one side, the other side, both. This first row, concave up like a cup. So all 3 of these satisfy that the second derivative at c is positive. Okay, really it's positive on the interval, but I will just write it for specific c. Okay, then this one, well, we have concave down, or the whole brown, right? Concave down, concave down, concave down. All 3 of these in the second row satisfy the second derivative at c is negative. Okay, these are all concave down and these are all concave up. But now let's look at columns, and this is where the first derivative and its sign comes into play. These two at c. Okay, well, you can think about drawing a tangent line. Slope is negative. Tangent line, slope is negative. Okay, you can also see the function is decreasing on the interval I have graphed. So this column satisfies the first derivative is negative, decreasing. Okay, similarly, pardon me, that's what happens when you use a marker as your tangent line. But here's my tangent line, slope is positive. Slope is positive. Or if you look at the purple, we see the function is increasing. Here we have first derivative at c, positive. Okay, But you see, the shapes, this is what I'm focused on, the shapes are slightly different. You can have concave up and decreasing, concave up and increasing, concave down, decreasing, concave down, increasing, like this. And finally, and this is an important third column, here I will draw it, tangent line, horizontal tangent, slope is 0. The third column satisfies the first derivative at C is 0. Now, let me make a quick comment about this right now. I'm going to come back to this later in the semester because I prefer first derivative test, which is where we use intervals of increasing and decreasing to figure out if you have a local max or local min. But what you notice here, we have a critical point at C. First derivative is 0. More importantly, first derivative is 0, and the second derivative is either positive or negative. And just knowing the first derivative is 0, second derivative positive, we see local min. First derivative is 0, second derivative is negative, we see local max. And technically, this is something called the second derivative test. I personally will get to this later in the semester because for now, we have a lot of ideas with increasing, decreasing, concave up and down, and all this. So I wait on the second derivative test to bring it up later, but we have discussed at least the idea by looking at the shape.